Math 1325, this is section 7.5. It's the final section of new material that we're going to be learning this semester. So all that remains after this is reviewing and testing for both the fourth test and the final exam. This is very similar to section 7.4. It's just that in 7.4, you're doing one function basically compared to the x-axis. And remember, we had to worry about when are we above the x-axis, when are we below the x-axis. In this section, it's two functions, and you're doing the area between them. But section 7.4 is the area between a curve and the x-axis. So the basic idea here is that the second function isn't always the x-axis. It'll be some other function instead. But just like you need to worry about when are you above or below the x-axis, here we need to worry about which function is above the other one. And it can switch in the middle of the interval as well. So problem number 1 says find the area between the curves x equals -2, x equals +2, y equals 3x, y equals x squared minus 4. So the x equals -2 and the x equals +2, those are two vertical lines, but that's going to end up being where the integral ranges between. We're going to do an integral between -2 and 2 potentially if one of these curves is always above the other one. If they switch places somewhere in between, then we'll have to set up separate integrals anytime it switches. So we'll check what the graph looks like, but then these two numbers are going to end up being here most likely. And even if it's not just them, it'll be those two plus some others potentially. So really what you want to concentrate on first are the two actual curves that are going on. Here we have one that's a line, y equals 3x. And then we have another one that's a parabola, y equals x squared minus 4. Okay, so we especially want to know what's happening between -2 and 2. So you could basically just plug in -2, -1, 0, 1, and 2 into both of these functions. 3 times -2 is -6. So when x is -2, y is -6 right here. When x is -1, the y would be -3. When x is 0, y is 0. And you also have a y-intercept of 0 and a slope of 3, so you're going up 3 over 1, up 3 over 1. So if I go up 3 over 1... up 3 over 1. So I have a line with a slope of 3, and it goes forever, but we only care about up to 2 right here. And it goes forever downward too, but only till -2 doesn't matter. So I got this line segment from -2 to +2. Okay, then x squared minus 4, well, minus 4, that would be the y-intercept here at -4. When x is 0, the y would be -4. If x was 1 or -1, either 1 or -1 squared are 1, and 1 minus 4 are -3. So there'll be a point right here and another one right there, right on top of the line. So far on the parabola, I have this much of the curve like that. And there's already a point of intersection right here. 2 squared is 4, and -2 squared is also 4. So both of those are 4 minus 4 or 0. So that's going to be here and here. Now the parabola keeps going forever, but we don't care about the rest of this out here or here. Okay, so we've drawn this from -2 to 2, and at first, if you go left to right from -2 until -1, the parabola is above the line. So there's an area right here between these curves. So I need to do an integral from -2 until I get to -1. And then what happens is you take the higher function, the ones above it, the x squared minus 4. That's going to be minus the line 3x. I'll put a parenthesis around it to emphasize it. But so in essence, we've been doing this since section 7.4. It's just in 7.4, this was always 0 right there. The x-axis is y equals 0. So in essence, you were doing a function minus 0 before, or potentially 0 minus a function if it was below the x-axis. So that's one half of the problem. But then from -1 all the way till 2, and it could keep going, except they're arbitrarily making me stop at 2. Then I've got this area right here, but the line is above the parabola on this whole portion. And here you don't need to worry about the x-axis. It's all about going between the two curves. So the x-axis is arbitrary. It doesn't even matter if we're at or near the x-axis on these problems. So basically what I do here, I need some more room. Let me rewrite this over here. I'm going to go from -2 to -1. And I'm going to have the parabola minus the line. And that'll be the smaller area. That'll be this tiny area right here. And then if I add a second integral, picking up at -1 and continuing to 2, and if I do the line minus the parabola, that'll be the other area. And if you always put the higher one in the graph first, then these will always be positive answers. So you never have to worry about any kind of negatives by doing that. As long as you need to know how the graph looks, because especially you need to know intersection points. That's where these curves can switch each other, switch places with which one's higher. And then we need to see which one's above the other one. And that's the one we always place first. So once you've settled that, then what I can do is I can just simplify this and put it back in a proper polynomial order. X squared minus 3x minus 4. This would be the first one to do. So do the antiderivative, x squared, that would be x to the third over 3. Minus 3x, increase the exponent by 1 to 2, divide by that exponent, and the constant will turn into a linear. And then we're going to evaluate this from -2 to -1. So big F of -1 minus big F of -2, that's the fundamental theorem of calculus. By plugging those in, then you get the area between the two curves. I'm just checking here, nothing reduces at all. Okay, so, and unfortunately we didn't get 0 to work with, so this will be a little messier, but I'm going to do f of -1. -1 cubed is -1, so we'll get a -1/3 there for this part. -1 squared is 1, times -3/2 is -3/2. And -1 times -4 is +4. So that bracket right there, that's f of -1. Big F of -1. Minus big F of -2. -2 cubed is -8 over 3. And then -2 squared is 4. Times 3 is 12. Divided by 2 is 6. So -6. And -2 times -4 is -8. Positive 8. So the negative right here makes all of these switch. This is going to switch to a +8/3. This will switch to a +6. And this one will switch to -8. And yes, you could combine this together and get -2 out of here if you want. So here, and this isn't, you could do this by hand easily, but just to speed things up, I'm going to type in all of this straight across. And if it's a decimal, then we can hit math, enter, enter. -1/3 minus 3 divided by 2 plus 4 plus 8 divided by 3 plus 6 minus 8. If I just type it all together, press enter, it's 2.833333 repeating. So math, enter, enter makes it 17/6. And they're always going to want it that way, not as a long decimal. So this answer so far is 17/6. The first half of this. And we could have got common denominators of 6 for everything if we didn't have a graphing calculator to do that. Okay, so now we're going to take that answer and add an answer for this part. So on this part, I'm going from -1 to +2. And now if I put this in order, the x squared would be -x squared first. The 3x would be positive. And the 4 would be a double negative and turn into a plus. In fact, if you have a polynomial like this, every term should be the opposite as it was over here. Here was x squared, here's -x squared. -3x, +3x. -4, +4. So at least the antiderivative is exactly the same except opposite signs. There's going to be a -x cubed over 3 plus a 3x squared over 2 plus a 4x. And then we are evaluating it. One of the two numbers is the same, -1, but the other one's different, +2. And I need to do big F of 2 minus big F of -1. Okay, so big F of 2. 2 cubed is 8, so I'll get a -8/3. 2 squared is 4, times 3 is 12, divided by 2 is 6, so that'll be +6. 2 times 4 is 8. Okay, so now that's big F of 2 right there, minus okay, so I'm just a little bothered by this almost matching but being a little bit different right there. Should be the same. Where did I get -6 here? -2 squared is 4. That is negative there. Positive here, huh? Positive, positive. Okay. Well, let's see if it comes out at the end. Okay, -1 cubed is -1, but then with this negative, it'll be a +1/3. -1 squared is 1, times 3/2 is 3/2. Well, I know why that's, yeah, okay. It's because I'm plugging 2 in, not -2. It's a different number I'm plugging in. Okay, so it was just bothering me for no reason, actually. And then -1 times 4 is -4. Okay, so always distribute this negative in, though. -1/3, -3/2. And then the -4 be +4. And then a graphing calculator can help with fractional ones. -8 divided by 3 for that part. +6 plus 8. -1/3, -1 divided by 3. -3 divided by 2, and +4. So that came out to exactly 13.5. But I'll still do math. Enter, enter. It's 27/2. And I could use my calculator for this too, but I'll just go ahead and multiply by 3/3 just to get it a common denominator with this one. So 27 times 3 is 81 over 6. Plus this 17 over 6 is 98 over 6. And both of those divide by 2, 49 over 3. But I could have typed 17 divided by 6 plus 27 divided by 2, where they don't have a common denominator. And then you get 16.33333, math, enter, enter. And there's the 49 over 3 that I just did by hand. So this can help speed things up just because you do get messy fractions sometimes. And these fractions aren't even all that bad. They're pretty small, 2/3 and 1/3 and 3/2. And so 49 over 3, that's the total area between those two curves in two different segments too. There's this little tiny segment, and then you have a separate area, so then you add the larger one. Combined, they make 49 over 3. Sometimes when you go from -2 to 2, one curve is always above the other one. Then you just have to do one integral. But if they crisscross and switch places, then you got to break it up into separate intervals each time they crisscross and change places. Okay, then sometimes they don't give you a amount to go through. Like the last problem went from -2 to +2. Now they're not saying that. Now they have just a quadratic, parabola graph, and a line. So then what's going to happen is that it'll be something like this, where they just cross twice and close each other up. So number 2, I've got a quadratic x squared minus 37. And I've got a line 11 minus 2x. So because I don't have a limited range of values to go between like before, then it's not going to really help. It could help a little, but it's not going to help me figure out the entire area if I just plug in like -2, -1, 0, 1. So here's what you do is you want to set these equal to each other. When do these two things equal each other? Since there's a square involved, they could equal each other twice. And that's what I'm assuming is if you take a parabola and draw a line through it, they can cross twice. And this could be the area that gets filled in like this. And then wherever the two cross points are, that'll be like our -2 and our +2 of the last problem. So we just basically have to figure it out ourselves where these things are crossing each other. The rest is not enclosed. This just keeps going up forever this way and forever that way. The rest is unenclosed. So we only want enclosed areas. So that's why they're not giving me where the x's are. I have to find them myself. So I would leave the x squared here, add the 2x over, subtract the 11, which would be -48. This is going to factor. When there's a negative in the back, you get one positive and one negative in your answer. Two numbers that multiply to 48, and the most common way to do that with single-digit numbers is 6 times 8. And what do you know? 8 minus 6, if you subtract them, gives you that +2. +8 and -6 is how you get +2 when you're subtracting, but -48 when you're multiplying. But these are the factors, so the zeros are -8 and +6. So this is x equals -8 right here. And this is x equals 6. A line can only cross a parabola at most twice. And I already solved for the only 2 times they're equal to each other. So there's no way for it to do it like what if I keep going out here? Will it ever come back and crisscross again? In this case, no. So I don't need to check any other spots to see does it crisscross anymore. I got the only 2 spots it crisscrosses, and I can see the line is above the parabola in that whole section. So all I'm going to need is one integral from -8 to 6. And the line should be above the parabola the entire time. I don't have to make two separate integrals like last time. And you just do the above function minus the below function. That's how the order always goes. There's an automatic minus right here. It's a difference between the functions. So once you set it up properly, which one's above the other one, then you can, if possible, you can combine stuff together and make this simpler to do before you do the antiderivative. So I would put it in polynomial form with the highest one first, negative x squared. This negative 2x. And then this negative 37 would be positive 37. Added to this 11 would make positive 48. In essence, it looks like what I got in order to factor it is just all opposite of that. Okay, do the antiderivative. The antiderivative of negative x squared is negative x to the third over 3. Minus 2x squared over 2, and those 2's could cancel. Plus 48x. And I just have to do one evaluation from negative 8 to 6. So big F of 6 minus big F of negative 8. Whatever that subtracts to, that's going to be the final answer. That's how much area will be in this curvy part right here. Okay, big F of 6. Maybe I'll put this here. 6 cubed is 216, so I'll get a negative 216 over 3. You often get over 3's on these because quadratics are going to go up to the third power when you're doing an antiderivative. And then this is just minus 6 squared minus 36. And then whatever 48 times 6 is, 288 plus 288. So that bracket right there that's big F of 6 right there. Minus, now I'm going to do big F of negative 8. So negative 8 cubed is negative 512. But then with this negative, it turns into positive 512 over 3. Negative 8 squared is 64, but then it's still negative. And what's 48 times negative 8? It would be negative 384. So without a graphing calculator, this can get challenging because you have to put all of these over 3. All 4 of these integers would have to be over 3. You could do that, but it just takes longer. So that's why if you have one of these, it helps just speed up, because the rest of this is just algebra work. It's not really the calculus side of this anymore. Negative 216 divided by 3 minus 36 plus 288. Okay, and then don't forget to distribute your negative in. So I need a negative 512 over 3, or minus 512 over 3. The minus a negative will be a plus 64. And same thing for this one, plus 384. If you just type it all in after switching the negatives on the last 3, then you can just press enter. You usually get a messy decimal. That's okay here. Math, enter, enter. It makes the algebra side of this problem a lot easier. 1372 over 3. 1372 over 3 amount of area. And it doesn't divide evenly. It's 457.33333 repeating. And they always frown upon decimal answers unless they're asking for it in a particular situation. So they would count that wrong and only count this fraction right. 1372 over 3. Type an integer. Oh, it does say a decimal. Okay. So you always got to read the blue. Did they say that last time too? No, see, last time I just said simplify your answer. So if they don't ask for a decimal, don't put it. But here they actually are asking for a decimal, strangely. So if it came out exactly, you would type an integer, but now they want a decimal round to the nearest tenth. Now they would count me wrong if I put 1372 over 3, they would actually count that wrong because they specifically asked for a decimal. You always got to do what they asked for. 457.3 to the nearest tenth. But usually that fraction's preferred, actually. See, here it says type an integer or a simplified fraction. Same kind of problem. I have a line and a parabola. This one's actually easier because it's not as messy as this one, had larger numbers in it. Should be a similar deal here. The y equals 10x is a line. The other one is a parabola, just literally x squared. So take these two things. When do they equal each other? When does 10x equal x squared? Well, I would get one side equal to 0, and I always like the quadratic part to be positive, so I would move the 10x over and make that negative. GCF of x, that would leave an x minus 10. So the two times these graphs cross each other are at 0, the origin, and at x equals 10. Because 10 squared is 100, and so is 10 times 10. So if you have a parabola, just the parent function of parabolas, x squared goes right through the origin like that. And then if you draw a line with a slope of 10, that'll go right through the origin too, because that is a y-intercept of 0. Boom, right there where they also cross, that's going to be the coordinate 10, 100. When x is 10, y is 100 in both of these functions. So they cross at 0, 0, and they cross at 10, 100. We don't really care about the y coordinates on these. It's all about the x's. The 0 and the 10 are the two important ones. And based on the graph I drew, the line is always above the parabola from 0 to 10. After 10, the parabola rises much faster, but these will just continue forever apart from each other and get wider and wider and wider. This will never be enclosed up here. And there's nothing enclosed over here, over here, over here. The only enclosed part is this little wedge between the line and the parabola, only between 0 and 10. It's the only time there's an enclosed segment. So that's the only area I have to find. I just need an integral from 0 to 10 and put the line above the parabola. So integral from 0 to 10, it's always nice when 0 is one of the numbers too. Integral from 0 to 10, I need the line 10x minus the parabola x squared in that order, because the line is above the parabola in the region I care about. Antiderivative of 10x is 10x squared over 2, and that could reduce to 5x squared, minus x cubed over 3, which doesn't reduce, and evaluate it from 0 to 10. So we need big F of 10 minus big F of 0. Big F of 10, 10 squared is 100. 100 times 5 is 500. Minus 10 cubed is 1,000 over 3. That bracket right there, that's big F of 10. Here's why we like big F of 0 many times. Because 0 squared is 0 times 5 is 0. And 0 cubed is 0 divided by 3 is 0. Often when you're doing big F of 0, often that whole bracket is all zeros, especially if you're dealing with polynomials. Now, if you're dealing with like exponentials, e to the x, then it wouldn't be 0. So don't just assume that's all zeros, but that happens a lot where you get all zeros here, so this whole part disappears. All I need to know is what does this equal? And you could get a common denominator, make 500, that could be 1,500 over 3. If you multiply top and bottom by 3, 1,500 over 3 minus 1,000 over 3 is 500 over 3. And it did say a simplified fraction, so this is what they're going to want. If you can't do that in your head, that's why this can help. 500 minus 1,000 divided by 3 is 166.66666, but math, enter, enter, turns it into 500 over 3. So the algebra part of this, once you've done the antiderivative, the rest of it's all algebra steps and calculations. And then that can be hard or easy depending on what happens with the antiderivatives. when there's fractions involved, it can be messy and maybe not hard, but hard enough that you can make mistakes and miss things. So if you have a graphing calculator, you can take all that out of the equation and make all that part easy, actually. Oops. So, it won't go. My computer locked up and I can't pull up the homework problem. Give it a second here. Okay, where'd it go then? Yeah, that was weird. Okay, so what did I say? 500 over 3? Okay, so let's do an exponential one then. Okay, this is like problem 1 where they're telling me go between -1 and +2. My first function is e to the x, and then I have a second one that's 3 minus e to the x. Type an exact answer in terms of e. Okay, I've lost my toolbar at the bottom. I can't pull things up so easily anymore. Okay, the computer is really acting weird today. So we were going from x equals -1 to x equals 2, I believe it was. And we had e to the x and 3 minus e to the x. So when does e to the x equal 3 minus e to the x? Or I could plug numbers in between -1 and 2 and try to figure out what's happening on the graphs. So what if I add e to the x over to the other side? Then I would get 2e to the x equals 3. Divide by 2. E to the x equals 3 halves. Then we could do a natural log to both sides to get the x out of the exponent. That would allow you to bring the x down, and e to the ln of e is 1, so that literally just makes x times 1 right here. So apparently these things cross each other once at ln of 3 halves. And ln of 3 halves is 0.405 approximately, which is in the range of -1 to 2. So that's the one time they crisscross each other. So I'm going to make 2 separate intervals. I'm going to need one going from -1 until I get to ln of 3 halves. And then we'll have to add a second one where we go from ln of 3/2 all the way to 2. And in one of them, it's going to be e to the x minus 3e to the x. The other one will be reversed. So we would definitely need to know, a good way to know is plug in 0. If I plug 0 in, 0 would be in this range right here because ln of 3/2 is about 0.4. When I plug 0 in for x, that's always easy to plug in, then I could tell which one of these is bigger. E to the 0 is 1. And if I get 1 here, 3 minus 1 is 2. So this function's bigger if I'm between -1 and ln of 3/2. So in the first one, we have to put this one first, since it's bigger, and this one second. And that means definitely the other one, I don't know if I should say definitely, but probably in the other one, it's the other way around. And if you did something like x equals 1, I guess you could use 1 because ln of 3/2 is only 0.4. So if I plugged 1 in, e to the 1 is about 2.7. And if you do 3 minus 2.7, that's 0.3. So yes, this one is bigger anytime you're past ln of 3/2. Okay, so in the top one, we're going to go from -1 to ln of 3/2. And I want to clean it up and I'm going to put 3 first. And then there's -1 and -1, there's -2 of those. So it's 3 minus 2 e to the x. And then in the other one, it's going from ln of 3/2 all the way to +2. And now it's going to be reversed. Now it's going to be 2 e to the x minus 3. Because I'm going to get an e to the x. I'm going to get another e to the x with that double negative on the outside. That's 2 of those. And then there'll be a -3 right there. Okay, so the antiderivative of 3 is 3x. That's just changing a constant to a linear. The antiderivative of e to the x is itself. And then divided by the derivative of the exponent, but the derivative of the exponent is 1, so it's just divided by 1. And then we need to evaluate that from ln of 3/2 to -1. So that's going to be a big F of ln of 3/2 minus big F of -1. Okay, for this one, you'll get the 2 e to the x first, and then a -3x, evaluated from ln 3/2 to 2. And that'll be a big F of 2 minus a big F of ln of 3/2. Okay, so ln of 3/2, I'm going to get I'll put a bracket here. 3, just literally put ln of 3/2 right where that x is. This is just some constant. I could get a decimal version in a calculator, but they probably don't want a decimal here. I'll check at the end. And then plug that in there. That's kind of nice when you have a e to the ln of something. The e and the ln part cancel out. So e to the ln of 3/2 is 3/2. So it's going to be -2 times 3/2. Since the e and the ln part will cancel. And then these 2's can even cancel. So it's 3 ln of 3/2 minus 3. That's big F of ln of 3/2. Minus big F of -1. That would be 3 times -1, -3, minus 2 times e to the -1. Okay, I'll keep going here and do f of 2, big F of 2. So plug a 2 in, you'll get 2e squared minus 6. There's big F of 2. That one wasn't bad. Again, when you plug ln of 3/2 in right for that x, the ln and e part will cancel, so it'll just be 2 times 3/2 with the 2's canceling again. And then you'll get minus 3 ln of 3/2. And this, well, I guess I can do that later. I was going to do this minus a negative 3 ln of 3/2 and try to combine it with this one way over here. So let me write down what we have. We have 3 ln of 3/2 right there. This is just a minus 3. Here you're going to get a positive 3. That's convenient because those now cancel out. Here you'll get a positive 2e to the negative 1. Or you could write it as 2 over e. Then there's a 2e squared. Those don't add together because they don't have the same exponents. There's a minus 6. And then this will turn into a minus 3. Okay, and then there's the plus 3 ln of 3/2. So this one and this one are like terms. They can add together and make 6 of those. I could definitely do the minus 6 and the minus 3 and get negative 9. And then these I don't think you can do anything with, other than maybe if you want to write 2 over e, if you like that better. 2 over e is the same thing as e, 2e to the negative 1. So again, there is decimal versions of e's and logs, but I don't think they want that here. So I can grab this. There it is. Okay. Type an exact answer in terms of e, although it doesn't say anything about ln's. So let's try this. 6 ln of 3/2. Whoops, no, not like that. 6 ln fraction 3/2 minus 9 plus 2e to the negative 1 plus 2e squared. And certainly we could type this into a calculator and get a decimal version if we really wanted to know what it was close to, but okay. Just leave it like that. It's messy, but there's some algebra involved in there and what stuff goes together and what doesn't, but that's all you can do with that problem. So it gets a little messy once you have exponentials in terms of the antiderivatives still having exponentials in them. Okay, the next 2 are good. Maybe it's next 3, actually. This is a nice concept in the business scenario. Okay, so let me show you what's happening here. If you have a supply curve in business, which they abbreviate S of Q, that's a supply curve. Usually supply goes up as you make more of your product. Then there's a demand curve, and the more of a product there is, the lower the demand goes for it. So usually the supply curve bends upward and the demand curve bends downward. These 2 curves can cross each other at a spot here, and sometimes they cross over here in the negative side that we don't care about because we can't make negative amounts of our product. So Q is the quantity of our product. This is the point of equilibrium right here. Point of equilibrium, it's the point where supply meets demand. Businesses want to reach that point because then you can maximize your profits that way. If there's too much demand, the supply runs low. If there's too much supply, the demand runs low, and then that's bad for business. So there's a certain X value that's actually a Q value. There's a certain Q quantity that makes that happen. And then F of Q would be whatever you plug Q into your function. So that's just a horizontal line right there. So this curve right here, once you draw this horizontal line in, which is the y coordinate of the point of equilibrium, the point of equilibrium is Q, comma, F of Q. Once you draw that graph, it separates this enclosed area into two portions, an above portion and a below portion. And there's these two concepts called the consumer's surplus and the producer's surplus. If you're familiar with real estate at all, they always talk about how it's a buyer's market or it's a seller's market. There's times where the buyers have the advantage. There's a time where the sellers have the advantage. This is a very similar idea. Consumers have the advantage sometimes. Producers have the advantage sometimes. So the goal is to find either one or both of these. I think the next three problems, one asks for the consumer's surplus, another one asks for the producers, and then the third one asks for both of them. Okay, so here they give me only the supply curve, and they tell me the supply and demand are in equilibrium at Q equals 4. They only want the producer's surplus in this problem. So I always remember it alphabetically, CP, alphabetically. They only want the producer's surplus in this problem. And I'm only given the supply curve. I'm not given the demand curve. Okay, so the supply curve is Q to the 7 halves plus 3Q to the 5 halves plus 50, and Q equals 4 is the point of equilibrium. Okay, so I need to figure out S of 4. S of 4 will be the y coordinate of the point of equilibrium. So with a graphing calculator, that's not bad. 4, actually I probably wouldn't even need a graphing calculator that much, because the divided by 2 of a fraction exponent, that's a square root. So the square root of 4 is 2. 2 to the 7th power. 2 to the 7th power. Plus 3 times... This will be 4, square root of 4 is 2. 2 to the 5th power. 2 to the 5th power. Okay, plus 50. So I plugged that in and I just got 274 for that. Okay, so the supply curve, this is a positive polynomial. Polynomials curve up like this. And then Q equals 4. I'll just mark off a spot and call that Q equals 4. If the demand curve was coming in, it would cross right there. So make a horizontal right there. This Y value is 274. And I need this area right here. That's the producer's surplus. The bottom area is the producer's. The top area below the demand curve, that's the consumer's surplus. So this is area between two curves, what this section's about. The first curve is actually a horizontal line, and that's the one that's above the supply curve. So I need to do an integral from 0 to 4, because you can't go into negative quantities. There's going to be a 0 to 4 integral. The horizontal 274 horizontal line, that's the above function, minus this supply curve, that's the below function. And once we calculate this, that's the answer. That's the producer's surplus, they call it. And I would do this and distribute this negative in here. make all three of these negative. So I'm going to go onto a new page to where we can see this better. So there'll be a negative s to the 7th, q, I'm sorry, negative q to the 7/2 power from 0 to 4. And then there'll be a negative 3, I don't know why I put an s here, this is supposed to be a q, negative 3q to the 5/2 power. And then this negative 50 can combine with the 274 to make 224. Positive 224. And q is the variable of interest, so we should put dq here rather than dx. So do your antiderivatives. Increase the exponent by 1. 7/2 plus 1 is 9/2, because you're adding 2 over 2, divided by 9/2. Minus 3q, add 2 over 2 to this and get 7 over 2. And then the 224 will just get a q attached to it. Evaluate this from 0 to 4, and 0 is nice because all three of these are going to be 0 when I plug 0 in. So big F of 0 is going to be all zeros. Big F of 4, whatever that is going to be the answer. So I'm going to do a square root of 4, which is 2, negative 2 to the 9th power over 9/2, or I could flip it around and make it times 2/9. Times 2/9. Minus, I'm going to flip this around, times 2/7. And then plug 4 into this q. The square root of 4 is 2. 2 to the 7th power. And then plus 224 times 4. All of this is big F of 4. Big F of 0 is literally 0 minus 0 plus 0. Anytime I plug 0 into these q's, it's going to make the whole part equal 0, since they're polynomials. Okay, so negative 2 to the 9th, negative 2 to the 9th, times 2/9. That's already messy. Minus 2 divided by 7 times 2 to the 7th. Plus 224 times 4. So I just went ahead and did it all at once since it started getting messy. And it's 745.6507937. Math, enter, enter. Although maybe they don't want this as a fraction. I think I just thought of this. This is all about money. So they're going to leave this as a decimal for sure and say $745. And just round to 2 for the dollars and cents, 65 cents. Yeah, I hit math, enter, enter, and it actually came out as a fraction. It came out as 46976 over 63. Who would have known to reduce it to that? But I don't think they're going to want that because this is all about money, actually. 745.65. Type an integer or decimal rounded to the hundredth. The hundredth is 2 decimal places. The reason they want that is because it's dollars and cents. $745.65. Okay, so 0 to 4, I did that. Plus, oh, did I write that wrong? No, that's plus, 7/2, 5/2, and 50. So let me double check. Did I do that value correct? 4 to the 7/2 plus 3 times 4 to the 5/2 plus 50. Oh yeah, I must have done that wrong, huh? Let me double check that. 4 raised to the 7/2 plus 3 times 4 raised to the 5 halves plus 50. No, it is 274. Okay, I thought maybe I did that wrong. 274 was right. 274 minus 50 is definitely 224. 7 halves. Increase it, flip it, 2/9. Maybe I typed that part in wrong. Let's try that again. I needed -2 to the 9th power. -2 to the 9th power times 2/9. And then there's a 2 to the 7th times -2/7. Oops. And then 224 times 4. So okay, so then there's a 224 times 4, and I need to subtract this other, no, not that answer. 896 minus 150.3492064. Yeah, I'm getting the same answer, so I definitely typed it in right. How far off am I? $745.65. It's off quite a bit, actually. Okay. Zero to 4. Square root of 4 is 2. 2 to the 9th. Negative. Divided by 9 halves. 2/9. Minus, oh, did I forget this 3 here? Maybe I think I forgot this 3 right here. Yeah, I never had the 3 in there anywhere. Okay, so that was it was a slight minor mistake. I forgot about my 3. So what I should be able to type is 2/9 times, let's do it this way, parenthesis -2 raised to the 9 halves power, no, to the 9th power. Okay, the 3 times 2/7, I'm just going to make that 6/7. So minus 6/7 times 2 to the 7th plus 224 times 4. So now I got 672. 672.507, so 0.51. 672.51, is that what they said it was? 672.51, yeah. So I forgot this 3 right there. So this 2/7 right here should have been a 6/7. If you change this to 6/7, then it works. So I overlooked my 3 right there while I was doing all that. But yeah, it just comes out as dollars and cents is what you do on those. So 672.51, that is correct. 672.51. Okay, let's do another one. This time, though, they want the consumer's surplus. That's the top part of the curve. And now they give me a demand function. Supply and demand are equilibrium of 3. Same exact question, except it's consumers instead of producers. And they give me the demand function instead of the supply function. So the demand function is 7,000 divided by 7q plus 3 squared, and q equals 3. 7q plus 3 squared, q equals 3. So if I plug 3 in, 7 times 3 is 21, plus 3 is 24. 24 squared is 576. 7,000 divided by 576. Unfortunately, it's not a nice answer. Okay, so we'll leave it 7,000 over 576, math, enter, enter. It's a messy fraction for some reason. So here's what the picture would look like. We're going to have a demand function coming down. And then Q equals 3, I'll just call that right here. So this horizontal is happening at a very weird y value of 1750 over 69. That's what I get when I plug 3 into the demand function. Okay, 1750 over 69. So that's the horizontal. The demand curve itself is above that, though. So the consumer surplus is this one. If I had a supply curve coming in like this, the producers would be down here. But we want the consumers, we only want this one this time. Last time we wanted producers. So now the integral is going to go from 0 to 3. And it's going to be the consumer, the demand curve first. The demand curve will be the higher one, the above one. Minus the horizontal, which is a weird constant. 1750 over 69. And then dq. Luckily, when we get to the plugging 0 and 3 in, the 0 part will be nice. Okay, if I was doing the antiderivative of this would be back to our substitution section of section 7.2. I would need to do a u substitution and let u equal the parenthesis part. And then du would equal 7 dq, because that's just a linear turning into a constant. And there is sort of a 7 here. There's a 7 times 1,000. I could break that up into a 7 times 1,000. So I would need to keep the 7 to use for du, but the 1,000's an extra constant. That would go out front. So I would have an extra constant of 1,000 out front. And then I would have 1 over u squared du. That's how this would work, like back in section 7.2. Everything's been accounted for that way. And this is an easy integral to do because you can change 1 over u squared to u to the negative 2. The other one you can put minus integral 1750 over 69 dq. That one you can just do as is because it doesn't need a substitution. So the antiderivative of negative 2, you increase the exponent by 1 to make it a negative 1 and then divide by negative 1. So I would have 1,000 u to the negative 1 divided by negative 1. And then minus this would turn into a linear. 1750 over 69q. And then both of these would be evaluated from 0 to 3 after I plug the u stuff back in. So now substitute back for u. Put 7q plus 3 where that u is. And then this negative 1 could make the 1,000 a negative 1,000. And then the u to the negative 1 could drop to the bottom and become positive 1. So then I could just have a 7q plus 3 down there. Minus 1750 over 69q. From 0 to 3. So big F of 3 minus big F of 0. But big F of 0 is going to be both 0. Well, actually, maybe not. Let's see, 0 here. I guess not. Okay. So you don't just assume that's always the case. So I'm going to plug 3 in right here and right here. So I would get negative 1,000. Seven times 3 is 21 plus 3 is 24. Minus this 1750 over 69. times 3, plugging the 3 in. That's big F of 3 right there. Minus big F of 0, which will not be all zeros because we don't have polynomials here for all of this part. This second part will be 0 because a fraction times 0 is 0. But if I put 0 in right here, the bottom will be 3 actually. So you'll get negative 1,000 over 3 plugging 0 in. Minus 0. That part would equal 0. Okay, so I've got negative 1,000 over 24. If I do 1750 times 3, that's 5250. That was a minus there. Okay, I couldn't tell what that was right there. That's minus. Okay, minus 5250 over 69. And then this double negative would turn into a positive 1,000 over 3. So here's where a graphing calculator definitely helps. Negative 1,000 divided by 24 minus 5250 divided by 69 plus 1,000 over 3. And I got 215.579, so I'll make it 0.58. So $215.58 is the consumer's surplus this time. $215.58. Nearest cent, they do want that. If I didn't mess up again with a little minor mistake somewhere. 7q plus 3 was my u substitution. 7dq u squared. 7 times 1,000. We need the 7 for the dq, but the 1,000's extra. 1 over u squared. So then u to the negative 2. Integral of u to the negative 2 is u to the negative 1 divided by negative 1. Then we have this extra part for the horizontal. Okay, so, nope, that wasn't it. Okay. 24 squared. 24 squared, yeah, it's 576. 7,000 divided by 576. This doesn't come out nicely, huh? Okay, I think I found it. It's apparently that part. I don't know how I got that, but I got when I did 7th, I was double checking that this horizontal value was right, and apparently it's not. I must have had a slight typo in the calculator at that point. Okay, so what I did again was I plugged 3 in for Q. 7 times 3 is 21, plus 3 is 24. 24 squared is 576. I had that. I remember having 7,000 over 576. And when I hit math, enter before, I thought it was 1750 over 69, but now I'm getting a totally different answer of 875 over 72. And it's still a weird number, but it's a totally different one. So I don't know what I must have hit wrong before. Okay, so what that would do is that would change this. Luckily, it's the easier part of this. So it's going to change this right here. And right there. So it would be right here too. So 875 over 72 needs to be right here. Luckily on this part it's 0, so it doesn't affect that part. 875 over 72 times 3. Math, enter, enter. So it's 875 over 24. So let's try it again from this point right here. Forget this. So negative 1,000 over 24 minus 875 over 24 plus 1,000 over 3. Okay. Second shot is 255, at least is a reasonable answer. 255.208 or maybe 21 cents. 255.21. 255.21. Yeah, okay. So again, it was a minor mistake of some kind. So somehow when I did 7,000 divided by 576, I got some weird fraction for that was just wrong somehow. But once I corrected it, then it was right. So the good thing is the process is right. I was just making one minor mistake after another. Here I forgot the 3, brain cramp mistake. And here I had a typo in my calculator. So once you make mistakes like that, you don't even know anything is wrong. And then 7 should be the one where we're doing both. Okay, so first we want to graph. We have a supply function. That's a quadratic. That's the one that curves upward, like a parabola. And then they have a negative parabola, so that's an upside down parabola. So number 7, we have q squared plus 13q for the supply curve. The demand curve has a negative q squared at the end, so that's what makes it upside down. 930 minus 19q. Okay, so just like the earlier problems, you want to set these equal to each other to figure out where do they crisscross. And it's often twice, but sometimes one's positive and one's negative. And the negative gets ignored because you can't have negative quantity of your product. So let's add the q squared over here. 2q squared. Let's add the 19q. That's 32q. And I'll subtract the 930 over. So that way it's equal to 0. Luckily all these divide by 2, so I can make these numbers all smaller, cut them all in half. And half of 930 is 465. Now that's still a little challenging to figure out what multiplies to 465 and adds up to 16. Actually, one will be positive, one will be negative. When it's too hard to do in your head like that, then this is a perfect case for either completing the square or quadratic formula. I would do completing the square because you have a nice 1q squared and an even q right here. So I'm going to move the 465 back over and put a plus blank there. Half of 16 is 8, so this will be q plus 8 squared. 8 squared is 64. So that's now 529. And that comes out evenly as a square root. The square root of 529 is exactly 23. So if I square root this, q plus 8 would equal plus and minus 23. So minus 8 right there. Negative 8 plus and minus 23. Negative 8 plus 23 is 15. But negative 8 minus 23 is negative 31. So those were the two numbers we needed. If we could have known that 15 times 31 was 465, that's what it would have taken to factor it, but who would have known that? But you can't have negative quantity, so you ignore that negative one. So what this is really saying is these two parabolas, the demand curve is coming down, the supply curve is going up, but over here they crisscross again over here. That's the negative 31 over there that we just don't care about. But here's the 15 that we need. So Q is 15, that's the point of equilibrium. And then if I can plug 15 into either one of the two original functions. And the consumer surplus is on top, the producers is on bottom. It won't matter which one of these two I plug 15 into, because it's going to give you the same answer for both of them. Because 15 is one of the two times that these two things equal each other. So if I do 15 squared plus 13 times 15, I plugged 15 into this supply function and got 420. If you plugged it in here, you would also get 420. It has to be the same. So 420 is the horizontal. Okay, so we're going to do this twice. The consumer's surplus, the consumer's the top one, that's going to be an integral from 0 to 15. And that would be the demand curve minus the horizontal of 420. So the demand curve is the 930 minus 19Q minus Q squared. That's the demand curve. And then minus the horizontal 420. And then when we do the producer's surplus, we'll go from 0 to 15 on that one. And that one's going to be the horizontal 420 minus the supply curve, which was Q squared plus 13Q. And this is all polynomials, so luckily the big F of 0 in each half will be all zeros. You might want to combine the 930 and the minus 420 first. So 0 to 15, that's 510 minus 19Q minus Q squared. So the antiderivative of that would be 510Q minus 19Q squared over 2 minus Q cubed over 3. Evaluate that from 0 to 15. In other words, just 15, because if you plug 0 in, all three parts are 0 when you plug 0 in. So if I put a 15 in each of these three Q's, that'll be the answer. And in the graphing calculator, you could just type it all in. 510 times 15 minus 19 times 15 squared divided by 2 minus 15 to the third power divided by 3. So I just got 4387.5, or 0.50 if I want to do dollars and cents. But it was exactly 0.5 in the calculator. So the consumer surplus would be 4387.50. Oh, first they want the graph. Okay. So I don't know why they're doing a dotted line. Oh, here it is. Okay. So S of Q is the solid line. D of Q is the dashed line. So the D is the one going downward. That's easy to remember. D goes down. The down is supposed to be the dashed line. So it's definitely not graph A or, okay, it's definitely not graph A. They correctly have it dashed going down on the other three. The y-intercept of this supply function actually is 0 because there is no plus anything at the end of this. So it should emanate from the origin, where this one's got a positive y-intercept, so this one's out. And the y-intercept of the demand function is 930, which is a little less than 1,000. This one seems to be way too less than 1,000. So it looks like it's graph B. The point of equilibrium is 15. That was the X, and the Y was 420 when I plugged 15 in. The consumer surplus, which was the one I just calculated, was $4,387.50. So now one last time, producer's surplus. So I just got to do this one. Here it's an integral from 0 to 15. I would do a negative q squared first, a negative 13q, and then the positive 420. So negative q to the third over 3 is the antiderivative, minus 13q squared over 2 plus 420q. And plugging 0 in, they're all 0. So I don't need to worry about the 0, so I'm just going to plug 15 in. Big F of 15 is going to be the answer. So negative 15 raised to the third power divided by 3 minus 13 times 15 squared over 2 plus 420 times 15. 3712.5. 3712.5. So then add a 0 to that to make it 50 cents. 3712 and 50 cents. So this 7's a good problem because you get to see everything in one problem. You had the drawing the graph and figuring out where the point of equilibrium is. And then you do your consumer surplus and your producer's surplus. Two different similar integrals. One is where the curve is above the horizontal. The other one, the horizontal is above the curve. Okay, finally, last problem. My worker sketches the curves. There's a square root and a linear one on a sheet of metal and cuts out the region. Find the area of the plate. Okay, so that's just area between two curves. We have y equals 6 square root of x, and y equals x over 2, which is the same thing as 1/2 x. So if you have a 6 square root of x goes like this, and then the 6 is just a vertical stretching of it. And then the line 1/2 x might come in like this. So it looks like this is the part they're cutting out right there. So we need to figure out when these things equal each other. It looks like they're going to equal each other at 0. And then the other, where do they equal each other? Right there is what I need to know. Because then I can do an integral from 0 to that with the curve above the line. So when does 6 square root of x equal x over 2 or 1/2 x? And one thing that might help is if you multiply both sides by 2, that gets rid of the fraction part of this. So 12 square root of x equals x. And then we could square both sides just to get rid of the radical. So that would make 144 x equals x squared. Let's get it equal to 0. X squared minus 144x. That has a GCF of x, leaving x minus 144. So it's apparently 144 is the other time. This time right here is when they equal 0. They both equal 0, and they both apparently equal 144. And if I plugged in something like 100, 100 divided by 2 is 50. The square root of 100 is 10. 10 times 6 is 60. So I just picked some number between 0 and 144, conveniently like 100. And the curve has a higher value than the line does. That's what I suspected from my sketch, but that was a way to confirm it. The curve is above the line until they meet again. They start together, and then they meet again at 144. And after 144, the line is always above the curve. But until 144, the curve is above the line. So we always have to know which one's above the other one. So I can do one integral from 0 to 144. And if I do the curve, the radical, minus the line, that would be the correct order. And then we could do two separate integrals. I'm going to do one with a 6 square root of x, but I'm going to make that x to the 1/2 instead of square root of x. And then I can do another one. You can break integrals into separate parts if their parts are added and subtracted. So then I could do a 1/2 x for the other one. So I'm just going to take, oh, actually it's minus right here. So I'm going to do the 6 square root of x as one integral, and then I'll do the x over 2 as another one, and there should be a minus between them, not a plus. Okay, so antiderivative here, 6x, increase the exponent by 1 to 3/2, and then divide by 3/2. And then you can flip the second and multiply, flip it to 2/3. And 6 reduces with 3 by 2. Oops, sorry, 2 would go here, not down there. And you could also think of it as 6 times 2 is 12. 12 divided by 3 is 4, or 2 times 2 is 4. So it's 4x to the 3/2. That's the first part. And then the antiderivative of 1/2 x is 1/2 x squared over 2. Which makes 1/4 x squared. And they both have the same 0 to 144, so they can share that here. And big F of 144 minus big F of 0. Big F of 0 will be 0 because 0 to any power is 0. So I really just need big F of 144. So 4 times 144 to the 3/2 power minus 1/4 times 144 squared. That's big F of 144. And big F of 0 is all zeros. So this divided by 2 part, that's a square root. The square root of 144 is 12. So 12 to the 3rd power. 1728 times 4, this part is 6912. 144 squared is over 20,000, divided by 4 is 5,184. So 6912 minus 5184, there would be a total area of 1728. This one was kind of nice how it came out. First time we had one that came out as an integer today. All the rest had decimals or fractions. 1728. Okay, so it doesn't say I have 100% here. That's because I missed that one from a brain cramp mistake. This one here. But once I got it wrong and saw what the answer was, then I found my mistake. I left off that 3 right there. So I could redo one if I wanted a higher grade, but at least you've seen how to do each one of those. So save. And now we're all done doing regular assignments. And there are 2 reviews and 2 tests to go. So the next video will do the review for test 4. And then you'll use that before you take test 4 on December 9th. December 9th is also when the related rates extra assignment is due, in addition to all these homeworks right here. And then the following week, we'll be able to do a lot slower, and we'll be able to do this review, and there's 30 problems in the review. I'll do 10 per day for 3 days, and that way you can go through the review nice and slowly. So you have review for test 4 and test 4, and then you have review for the final and final. That's all that's left. We've covered every homework problem now. So see you next time for review number 4.